today, and we'll get it done, is to finish what we need to get completed by this week, right? So our homework is up to chapter 3, patterns in scatter plots and correlation. And we did an awful lot of notes yesterday with names of things. So we know about linear and collinear and strong and weak, and we know a bit about outliers. We know we did actually, if I recollect, didn't we also use SALT to do scatter plots for us? And we looked at questions where you'd see a scatter plot and you'd answer questions from that scatter plot. So we've done quite a lot, and you might think that's kind of everything covered, but actually we've still got a lot to do from that one section. There's a lot in it, essentially. So I want you, we'll start off, it's more notes again. So imagine that going along the x-axis, we'll stick to my story about the age of an animal again. So this is the age of an animal, and we'll do it in months again. And vertically, we'll do its weight. And this time, just to be different, we'll make it a very small animal. So this is its weight in ounces. So the units are age in month against weight, and they collected a whole, I don't know, hundreds and hundreds of these guys, these little creatures. And there's 1 month old, 2 month old, 3 month old, 4 month old, say 5 months. And it was 1, 2, 3, 4, 5 ounces, 6, 7, 8. So you can imagine it's not a very big creature, some kind of mouse, maybe, tiny little creature. And we collected data, and it ended up looking something like this. Nothing too surprising, right? Since I've got this data set up, let's go through some of the vocabulary that we used yesterday to describe this. Can you give me any of the words that we used yesterday to describe this scatter plot?
Positive.
Okay, I agree. So positive is good. I'm just going to add an extra word.
Linear.
Linear.
I agree with that. Wouldn't the linear be the shape, essentially? And one more thing that we would use to describe that.
Strong.
Yeah, I'd probably go strong. Some of you might have chosen to call it moderate. It's almost a judgment call, right? You know, about how close to the dots need to be. Would you agree that this particular scatter plot has no outliers? We're comfortable with that. Now, we have 2 variables here. One of them is called the response variable, and one of them is called the explanatory variable. So let me tell you who is who. I want you to think of the explanatory variable as being whatever is on the horizontal or the x-axis. And then the vertical one is called the response variable. So I'm just adding some more vocabulary. So in this story, the explanatory variable is the age and the response variable is the weight. Right? So you found a creature that was 4 months old and you weighed it. You found another creature that was 2 months old and you weighed it. The first thing is what's called the explanatory variable, and the second one is, okay, for that 4 month or whatever old mouse, what did it weigh? The response is, what did it weigh? Right? You okay with that new term, response and explanatory? rather than X and Y axis. Okay. So let me zoom over to some scatter plots and just ask you what the response variable name is. What is it? And what is the explanatory one? Okay, so here's one about January temperatures and latitude. Which one of those two things is the explanatory variable?
Latitude.
And so the response variable would be January temperatures. Okay, scroll somewhere. Here is one to do with the houses. Which one of those guys is the explanatory variable?
Square footage.
And response variable.
Asking price.
Right. Would you say that that's probably one of the easiest questions you're going to be able to answer? Right. Now, suppose they do not give you the information as a scatter plot. They just give you a table like I have here. Okay, so there's the two numbers that are going to become a scatter plot, but all you've got right now is the numbers in the table. Which one of them is the explanatory variable?
The square foot.
Okay, and so the response is asking price. It's dead easy to tell once you've done a couple. Isn't the one on the left-hand side typically going to be the X value? So that's the explanatory variable. And the one to the right of it is going to be your Y. And that's going to be, think XY, first, second. Does that help? XY, first, second, explanatory response. Now, I don't think I'll find one. Well, maybe I can. If I can, that'd be great. If not, I'll just pretend I've got one. Now, okay. Can you imagine that I've got a table going horizontally? Right? And so, at the top, you've got age, and underneath it, you've got money. So maybe it's the age of a person and how much salary they make, right? Age in the top, money in the bottom. Which one of them is going to be the explanatory variable?
The age would be explanatory.
Right. So when the table goes this way, the guy on top is the X, the one underneath it is the Y. The guy in the top we called explanatory. The one in the bottom is called response. Are you comfortable then, no matter how they orientate the table, you can still, if you look carefully, you can figure out which is the response and which is the explanatory variables. Does that seem okay? Right. So that was a term that we haven't brought to bear. So with this same diagram, we're going to introduce a new guy, a couple of new guys actually. This is the first new guy. I'm not drawing this very well, so I'm going to have to add a couple more dots so it looks more realistic. If you've got a nice linear data, which this is, wouldn't it be possible to draw a straight line through it? It won't be a perfect straight line, right? Because a lot of dots, you can't go through all the dots, right? Because they're not in a straight line. But would you agree that there's a general straight line? I better go to the picture. I've realized I'm in the wrong
I'm not
place.
seeing a plot.
Yeah, exactly. Right. Let's hunker back to this, right? Yeah. Would you agree you can draw a straight line through some data points, right? That straight line is very important. It has lots of names, unfortunately, and it depends on which textbook you're reading it from. And it sometimes, even within a textbook, they give it different names. So I'm going to give you as many different names for that straight line, so that no matter what video that you watch, you know, if you go online and you see a video and they use this term, you'll know it's the same guy. This line is called, this is one of its names, the best fitting line. Actually, that's a pretty good name. Would you agree that's a good name to call it, right? Here's less obvious names. It's called the least square line. It's also called a regression line. It's also called correlation line. If I thought of any more, linear, best fit, least square, regression line, correlation line, right? That's all I can think of. I might think of another one 10 minutes from now, and if I do, I'll come back. Well, you just realize that it's the same line. They just call it different things depending on who's writing the textbook. Right? The lines that you're going to see, I hope, is going to be this name here, regression line. I like this name, so I'm going to keep that one. But you're probably going to find it called the regression line, right? I believe that's what this textbook calls it.
I've heard or seen, if I'm understanding this correctly, that being called a trend line also. Is that correct?
Well, you've just found a line, a term I have not met before, but it won't surprise me.
It's used in Excel spreadsheets a lot.
There you go. And I guess if we keep looking, couldn't we probably find 3 or 4 more ones? As long as whenever you see it, you all say, hey, it's just the name they give to this line, right? It's not that these are different things. Aren't these the same thing with different names? Right, so I think I'll stick to the regression line because I think that's what this textbook uses. So at least I'll be consistent when you see questions in the book. Now, that regression line is unique. In other words, there is one line that does a better job than any of the other lines. So you might think, well, couldn't you just tweak it a little bit this way, a little bit this way, drop it down a little bit, drop it up a bit? Wouldn't they all do just as good? And the answer is, well, they all do reasonably good. But this one does the best. That's why I like the name best fitting line. It kind of gives me an idea. And it's very, very difficult to get the equation of that line by hand. So we're never going to do it. Salt is going to give us the equation of that line. So I am going to do a little bit of revision on straight lines before we start focusing on this particular kind of line. Way back in Math 94, when you had X and Y axes, and I'm just randomly drawing a line like that, wouldn't its equation look something like this? 2x plus 3. Wouldn't that be the equation of a line? That's the typical way equations of lines are written, right? The y coordinate is twice the x coordinate plus 3. Does that ring some bells? Equations of lines? Okay. Just introducing you to terms that are going to appear in this work as well. This point here is very important. It's called the y-intercept. This guy down here is called the x-intercept, but I'm not going to talk about him because we don't use him. But we do use y-intercept a lot in these questions. And then there's another term, and it's called the slope. And in this case, isn't the slope 2? And in this case, isn't the y-intercept at 3? Are you comfortable? The y-intercept is the place where it crosses the y-axis, and the slope is how steep the line is, right? A slope of 3 would be really steep, wouldn't it? And a slope of 1/2 would be quite shallow. And you can tell the slope of a line because it's a number next to the x. It's what we call the coefficient of x. Is all of this familiar? I'm not saying anything you've never seen, right? I'm just recapping so that when I use terms, you're going to feel comfortable about it. So let's suppose somehow or other, by magic, I give you the equation of this line. If I gave it to you in terms of x's and y's, it might look like y equals 1.3x minus 1, right? Okay, something like that, okay? We won't write it like that. Isn't our response variable the y-axis weight? So what we will do is we will call it weight, and we won't call it 1.3x, we will call it 1.3h, take away 1. So that's how you would write it for the equation of a line. can you see how we will write it in statistics? Won't it look much more like a formula and less like the equation in Math 94? But isn't y the explanatory variable weight, and isn't age x perfectly matched? Are you comfortable that this equation can be written like this? Are we good? Okay. So forget about that dotted guy. Let's suppose I've got some data. And the data is the price of a house. And it's equal to 32,000 plus 150 times the area. And that would be my my correlation line, right? My regression. Now, if I gave you that formula, and this one is to do with, you remember the scatter plot where we did the square footage and we did the price, and it kind of looked like that, and we could use it to predict the price. So if I gave you this equation, couldn't you use it to make some predictions about what the estimated price of a house is? Right, this isn't the guaranteed what you'd sell it for, but it being close to it. So it's not uncommon, for instance, for this formula to be written in a number of ways. You will see sometimes people put the word estimated in front of the word price. You will also see it written like this. So I just want to show you different ways of writing the exact same equation down. Now, I think price equals is pretty obvious. Would you agree estimated price is just maybe being a little bit more pernickety, right? And then this funny thing, which is price with a little funny hat on it. You say that out loud as price hat. It's a funny way to say it. That just means estimated price. But I guess what people don't like using words, so they use a little symbol. So you use that symbol to represent estimated. So estimated price, and then you read the formula. So suppose I had a house, right? And this house was 1,000 square feet. Then couldn't I use this formula to estimate or predict what we think that house would sell for? Well, according to our formula, the estimated price is 32,000 plus 150 times the area. And that ends up being 182,000. Are you comfortable with how we could use this formula to predict the price of a 1,200 square foot house or a 2,000 square foot house? That makes sense? If you've got the equation, you are good to go. So can you imagine you get a question where you know this formula or Salt gave it to you? We'll show you how you do that. And once you've got this formula, can't you then simply just use it to calculate estimated price of any house up to a reasonable amount? So the estimated price is 32,000 plus 150 times area. These two numbers, if I wrote this down as y equals 32,000 plus 150x, right? If I wrote it with x's and y's, wouldn't it look like that? These two numbers correspond to y-intercept and slope. The y-intercept is 32,000 and the slope in this case is 150. these two numbers sometimes have quite interesting meanings. Let's look at the y-intercept. If I drew this data, it would look something like this. And that guy there would be at 32,000, right? This is the price of the house here. And along here would be the area. What does that 32,000 tell us about buying a house in this area?
That's the price of the land by itself.
Yeah. Is it not the price when there's the area of the house is zero? In other words, there's no house. So if you were just going to buy a plot of land in this area, it cost you 32,000 for the piece of land. Right. Nailed it. Now the slope is 150. Now, if you take any point and you move 1 square foot, you will go up by $150. So the slope is actually telling us the average price per square foot. Does that make sense? One of the things you can do when you want to see how expensive a house is, right, is, and they very often will tell you this, they will tell you the price per square foot. So I'll make up numbers here. Do you know if you were buying a house in East Bremerton, a typical house might be $150 per square foot, right? That's the average square price. So you want to buy a square foot of house, it costs you 150. You want to buy 100 square foot, you know, and so on and so forth. So in Bremerton, that might end up being $150 per square foot. Of course, if you try to buy the same type of house, what do you think it might cost you in Bainbridge Island? More, less, or the same?
More.
More. And I'm making this up, but it might be $300 per square foot. Do you see how knowing that number, which is essentially the slope of the equation, doesn't that give you a pretty good impression of how expensive houses are in various places? So imagine you got, this was Bremerton houses, but you did a scatter plot for Bainbridge Island, and you did a scatter plot for New York. Oh God in Himmel, can you imagine what that would look like? Yeah. It'd be thousands of dollars per square foot, right? Or what about California? Isn't that just as bad now? Yeah, in certain places. So the y-intercept in this context is telling me what the price would be with 0 square footage, which becomes in English the price of the land. In this one here, and the slope is telling us what 1 extra square foot, another square foot of land, house is going to cost you 150 or 300, whatever it might be. So we might call that something like the average increase per square foot. So far, so good? Right, now looking at question 8, so I'm just going to write this one down. In question 8, they've got the average weight of someone, should really be the predicted average weight, but we'll call it the average weight. And the number is negative 250 plus 6 times their height. And estimate the average height of somebody who, oh, let's think, 62 inches, right? What would a 5'2" person, what would their average weight be? Well, I'll call it average weight for short. Negative 250 plus 6 times, I think I said 62 inches. So I go to my calculator and I go negative 250 plus 6 times 52, and God, that's stupid. Okay. £62. Okay, what would the average weight of someone who is 6 feet tall be? -250 plus 6 times 72, and I get, now that's much more reasonable, would you agree? This formula that they've given us, and I'm just writing down the formula that they've got, would you agree that it's probably quite accurate for tall people, right? 6 foot, that kind of height, but it's very inaccurate for short people, right? I mean, 62 is 5'2", right? You're not tiny, and I definitely know you're not going to weigh 62 pounds. So can you see that this formula, we sometimes call them models, is not very good for short people, and it's probably quite good for tall people. That's just the conclusions I've got there. Now, this number here is the slope. Since the slope is 6, essentially, doesn't that mean for every extra 1 inch in height, the weight increases by 6 pounds. So that there is telling you for every extra 1 inch in height, won't you gain another 6 pounds in average weight? So if you found somebody who was 70 inches tall, and then you found someone who was 71 inches tall, wouldn't the difference be just 6 inches, right? There'd be 6 pounds, I should say, more. That kind of makes sense. Do you agree? If all things remain the same, if you're an inch taller, wouldn't you probably be a little bit heavier? Because there's more of you, right, going vertical. Right? As long as you don't get fatter or skinnier while you do it. Are we good with that? So if I give you a formula, you can use it to calculate things, estimated weight in this case. Sometimes the estimate's going to be pretty horrible. Sometimes pretty good, right? Common sense will tell you which. Here's a version from question 10. The average math score that someone gets is 575. I think this is SAT math to be precise. Take away 1.11% that took the exam. So we did one. Remember, we did the scatter plot that was all the states in America, and it looked like that. And along here, we had the percentage who took the test. And up here, we had their average SAT scores. You remember the one that looked like that? So now that they've given me a formula, I can use this formula, right, to make certain predictions. How about there's a state in America where only 9% of the students took the test. And I'd like to know what the SAT, average SAT for these students in this state would be. So their average SAT in math would be 575, take away 1.11 times 9. And this gives me 575, take away 1.11 times 9. And the answer is that they would probably get round about 565. Couldn't I use that for a state where 80% of the students took the test, or 2% of them took the test? Can you see, replace this by 80 and calculate it would give you that answer. If you wanted to know a state that only 2% took the test, put 2 in here and you'd get a different answer. What you're looking at here is basically the equation of that line that goes like that. What would be the number up here based on this equation? What would be that number right up there?
575.
Isn't that what we would call the y-intercept? And wouldn't the slope be negative 1.11? Can't I tell that just by looking at the formula? For every 1% more people that take the test, won't their SAT fall by 1.11? Isn't that a way of interpreting this? For every extra 1% who take the SAT, right, who sit it and took it, their score, the average score, will reduce by 1.11, right? Reduce because it's negative, 1.11 tells them that. Now, this y-intercept doesn't have any sensible meaning here, because wouldn't that be, if nobody took the test, wouldn't the average be 575? Would you agree that kind of doesn't make sense? Because if nobody took the test, there wouldn't be any average in the first place. Not all y-intercepts make sense. All slopes make sense, right? They have some kind of mean something, but not every y-intercept necessarily is sensible. So far, so good. Right. Let's suppose I had the house one again, a different story. Predicted price for a house, and let's say it's 50,000 this time, plus 120 times the area. And I used it to predict a house that had 2,000 square feet, right? So there was a house that had 2,000 square feet, and I want to know what it sold. It probably, let's phrase it that way, would sell for. So it's 50,000 plus 120 times 2,000. That's 440. That would end up being $490,000. We would call that our, I guess, our predicted price, right? So far, so good. Now, let's suppose that this house sold, right? So it's not a theory now. Would you expect it to sell for exactly 490,000 in real life? No. Sometimes people are willing to spend a little bit more, right? There's a bidding war going on. Sometimes people put in a lower offer and you accept it, right? So there's going to be some wiggle room. So let's suppose that in my story, the actual, right, the real price ended up being $500,000. So there was a little bit of a bidding war going on. So they actually managed to sell their house for a little bit extra. That would not be unreasonable. Would you accept that that could happen sometimes, right? In fact, isn't the predicted price just a kind of ballpark figure? The price of any given house will vary a little bit, hopefully not too much from that price. So we now have a new guy called residual. I want you to think of residual as the error. What did you get wrong? How far out were you? How would you be able to tell in my story here where the predicted price was 490, but they actually sold it for 500? How we would calculate the residual, the error? What would you do?
Subtract them.
And we're going to subtract them with the actual price, take away the predicted price. So you always put the real answer, right? The thing that did happen first. In this case, 500,000. And then you subtract what the predicted thing was. And this particular one ended up being $10,000. And we call that the residual. Now, if you have got a good model, wouldn't you want these residuals to be nice and small? Because that means you predicted a price and kind of sort of that's what you got. Wouldn't you want that to be the case? Does that make sense? If you had a model and people said, okay, I used your model to predict what the last 100 houses in Bremerton sold for, and your model compared to the real value, the residuals were horrible. You were 50,000 out, you were 100,000 out, you were 90,000 out. Wouldn't you be not very happy about using that model in the future? Because people don't want to use you if you say, oh yeah, I'll be able to get 500,000 for it, and they end up selling it for 400. Aren't you going to feel really gypped about it? You know, that guy said he could sell it for this, that's the predicted answer, and it didn't even sell anywhere near it. So you don't want big residuals, because what that is telling us is that the straight line is not a very good fit for the data. Now, it doesn't mean that the guy made a mistake. Let me show you two very baby situations to show you why you can have a problem. Can you imagine that there's a town or a village or whatever you want to call it, someplace, and this is what the prices look like, right? There's the area, and that's the price. Would you agree that's nice and linear and pretty strong? Can you imagine then that when you do the line, won't that line be darn close to the real answer every single time? Won't the residuals be nice and small? But in some places, can you imagine in this world, isn't there a very good chance that there's a reasonable number of answers that are going to be quite far away, right, from the predicted answer? So what that is telling us here is that some models are really good, right? All the data is nice, close together, like a linear. And when you've got a model like that, wouldn't you be comfortable about using this formula to predict the house value? But in some places, put some more dots in here, isn't there a lot of variation in what the house looks like and how much it costs? And wouldn't this model not be a very good predictor of the real price? And maybe you shouldn't even use it. You know, find some other way. One of the classic ways of doing things is called comparables. So what you try and do is find 2 or 3 houses darn close to what yours looks like, right? Same kind of size, same kind of view, same kind of condition, as many things as you can. And your house will probably sell something close to what those sold for. So that would be a different strategy, right? Wouldn't it be nice if there was a number that we could have that tells us which of these two situations that we've got? And you might say, well, couldn't I just do a scatter plot and look? Well, you could, but the problem with scatter plots is scale. Do you know if you use a different scale, you can make data look much more spread out than it really is, or very close? You know, if I did one box is 10 and I did one box is 100, wouldn't one of them look all over the place and the other look quite tight? And so scale is a problem. So that's why we don't tend to just look at the scatter plots, because depends on what scale you use, it could look better or worse than it truly is. We have a new guy in town, and he is called the correlation coefficient. And he's always called little I. At least it better be, because that's what I call it. And the correlation coefficient is a number that tells us how good the data is to being a straight line. So it's a number that tells us how good the data is to being a straight line. Salt will get us that. As soon as I finish this, I'm going to go in and show you one in salt. So you are not going to get this yourself. You're going to use salt. But let's show you what it looks like. The correlation coefficient, R, always takes values between 1 and -1. It's always going to be a number somewhere between 1 and -1. The perfect value is 1. When R is equal to 1, that looks like an A. I'll do it again. When R is equal to 1, that looks better. You have a perfect positive straight line. What do you think the R value would be for a line that looks like this guy? If +1 means a perfect positive line, what does a perfect negative line look like?
R equals -1.
Agreed. Now, if you've got some data that looks somebody got a big shotgun and just blasted it, you know, with buckshot, one of those things, would you agree that there's no obvious direction to it? And that's what 0 looks like. So a correlation R equals 0 essentially means there's nothing to see here, right? Would you agree I could draw a line like this, or a line like this, or a line like this, or any other line? Would you agree that every line is just as bad or as good as any other line in that data? Because there's nothing going on, right? It's all over the place. Now, here's a little rule of thumb. If you calculate the correlation coefficient R for straight line data, and this is only for straight line data, if you get a number between 0.9 and 1, then you are looking at a nice strong line, right? Darn close to being really tight. Between 0.7 and 0.9, it's going to be moderate. And 0.1 to 0.6 is going to be weak. Do you know if you get anything, I guess I should put this in, but if you get anything that's less than say 0.1, there's none. There isn't actually anything going on. It's just a big blob of dots, right? Isn't it nice now that we've got a number rather than us saying moderately strong and weak? So let's do a test on that. I collected some data and somehow or other I found its correlation coefficient, and it ended up being these numbers. So I did it for different things. And this one is 0.75, 0.91, 0.3, and 0.09. How would you describe the first scatter plot if that was its correlation coefficient?
Moderate.
You see, moderate. Agreed? What about 0.91, a correlation coefficient of 0.91? What would you call that?
Strong.
What about 0.3?
Weak.
And last but not least, suppose you got a nothing point nothing 9 or something like that.
None.
I wouldn't even say it was linear anymore. Would you agree? It's just, it's that guy, right? So it's got none. Remember, we had the problem with outliers, and it was a judgment call. And then we told you about the IQR test, and then the ±3 standard deviation test. Wasn't life so much easier when you had numbers and you didn't need to do a judgment call? Isn't it now easier if you can find the R value to not have a judgment call anymore? Now, you know, different textbooks might tweak these numbers a little bit, but that's fine. At least we've got some numbers to work with. So let's look at, for the last few moments, you can hang in there. Let's show you how to calculate the correlation coefficient and the equation. And I promised you that we were going to use salt. So let's find salt and do it. Come on, there we go. Right. Oh, perfect. Square footage. Are you looking at square footage question? Right, this guy here. So what I'm going to shrink it back a little bit so we can maybe see everything at once. If you hit the salt button, you get this guy. I'm going to go charts and graphs. Right. I'm going to hit scatter plot and square footage and asking price. Now, down at the bottom, there's a whole load of guys, right? And can you see the correlation is 0.9102? You see it? Correlation. So wouldn't that be a pretty strong relationship? Now, you might look at that scatter plot and say that doesn't look very strong, but you got to remember scale screws things up. So do outliers. Now, it has here slope and then intercept. You see those two guys? The guy that's called intercept is the number, and the guy that's called slope is the 0.28x guy. So it'd be 0.2808 times area. And the reason why that's a decimal is that if your answer is 22, it means 22,000, right? So it's just thousands. And that's it. That's how you get all the guys you want. Now, if I leave this guy and we'll look at some of the later questions, do you see they just give you the formula and they get you to use it? So that's going to be pretty straightforward, I hope. They give you the formula and then you get to use it. They give you the formula and for the most part, you get to use it. We've covered that before. Here is a relationship that looks like math, right? With X's and Y's. In this relationship between X and Y, is it a deterministic or a statistical relationship? Oh, I haven't covered that word. If you use X's and Y's, or you use price and square foot, you're looking at the information in two different ways. When you use X's and Y's, you are basically saying math 94, 99, and they are called deterministic. If you were saying predicted price, blah, blah, times area, right? If you wrote it that way, then you'd be using it as a statistical thing. So apart from that, plug in the numbers and get your answer. There's another one. Oh, and you could use the fact that it's centigrade. Has this got a cat? No, this one gives you a formula. This one gives you a formula. And oops. Okay, I've got this guy in front of me. It's to do with pulse rate. Looking at this equation here, what is the number that's the pulse? What is the slope, I should say?
0.894.
Right. Isn't that always a number next to the explanatory variable? What's the y-intercept here, if they bother to ask you?
17.8.
Right. So we're comfortable about the number on its own is the y-intercept. The number next to the variable is what we would describe as being the slope. Here are some lines that you could play about with doing it. Does this have salt? Oh, no. Equation and use it. Oh, do you see my funny little y hat? Do you see it there? In a little hat? Then that's good. Because won't the slope here be negative 2.34, for example? And that